Luc, on n'entend pas.
Branché. Voilà, j'ai branché là. Est-ce que c'est mieux?
Ouais, c'est bon, on entend. C'est
Ah,
parfait.
super. Donc, il faut que je retrouve le truc pour enlever la barre.
Plus.
Ah, c'était là. Ouais.
Masquer.
Masqué. Hop. Voilà, donc c'est reparti. Donc, je recommence. On a le plaisir d'accueillir Catalina LOZADA, qui est professeure à l'Université pontificale à Bogota, de l'Université Javeriana. Et en fait, Catalina est une vieille connaissance maintenant, enfin, si je puis dire, puisqu'elle a passé son doctorat en 2016, un doctorat en co-tutelle entre la Universidad de los Andes à Bogota et l'École centrale de Nantes, ici. Donc, elle avait soutenu dans cet amphithéâtre, ici, bâtiment Viarme, sur le campus de Nantes. Voilà, donc Catalina est venue cette année en visite là, pour un mois, suite à un petit appel d'offres organisé par l'ambassade de France à Bogota pour monter un projet, en fait, dont on aura peut-être l'occasion de parler après la présentation. Voilà. Et, euh, et donc, ben, non, j'avais autre chose à dire, c'est que Catalina est aussi une géotechnicienne qui fait de la modélisation physique. Et elle a eu, dans un poste précédent, le plaisir aussi de monter une centrifugeuse nouvelle donc à l'université où elle a travaillé juste avant. Voilà, donc maintenant, je vais te laisser la parole, Catalina, s'il te plaît.
Merci.
Voilà.
Merci. Thank you for coming. I think I will speak in English for everybody can understand. The title of this presentation is about physical modeling of slope stability considering the effect of vegetation and soil type. I can change. Mhm. I'm coming from Colombia. It is a country located in South America, in the north of South America. I'm coming from Bogota. Bogota is a city of almost 8 millions of inhabitants, and we have an altitude of 2,500 meters above mean sea level. This is the university I'm coming. It's an university, a Catholic university, most of one of the oldest university in Colombia. There are almost 3,000 students and 3,000 faculty members. I belong from civil engineering department. This building, as you see here, it's the laboratory engineering building. We have many facilities. Okay. There is a big reaction wall that for simulating buildings at the real scale to apply laws with these actuators. There is also a pavement track to simulate fatigue and long-term behavior of fuel scale pavement structures. And also we have a laboratory from geotechnical engineering. We have a civil cyclic triaxial test, Bender elements, resonant columns, simple shear cyclic test, and hollow cylinder test, among others. A large shear test to test geosynthetics also. I am a member of the research group CECATA, it's called Center for Studies in Roads and Transportation and Related Fields. We are 6 and 7 professors. Freddy, he did his PhD here a long time ago. I don't know, in the fatigue. I don't know if you know. Okay. So we have 3 research investigation lines, and I'm working in 2 comprehensive development of Colombian infrastructure, analysis and modeling of geotechnical processes. The objective of this group is to develop, validate, transfer, and adopt technologies in areas related to infrastructure. At the first part of in this presentation, I would like to show you some challenges we are facing in Colombia. We have the Andes mountain that begins in Argentina, at the South America, in the south of South America, and in Colombia is divided by 3 mountain ranges. We call Eastern Mountain Range, Central and Western Mountain Range. And Bogota, for example, it's located here in the Eastern Mountain Range. So we face many problems about slope stability. So in urban area, because Bogota is located just here in the border of the mountain. In fact, we have a very deep clay deposit, but we have also problems of slope stability. And also highway infrastructure, that because the main cities in Colombia are located in the mountains, in the Andes mountain. So I want to show you a urban problem that we visit with the students. There are many exploitations pits for construction of the city. There are more than 100 quarries at different stages of exploitation. Right now, there is not permitted, but there are many environmental problems about this, and also slope stability problems, because many houses are constructed close to these older quarries. This is there are 2 views with Google Earth. We can see the environmental problems. And we just visit some places that the mayor of Bogota are trying to recover. So we see with the students stabilization techniques from the slopes. As you can see here, gabions, soil nailings, and some protection to control erosion. Also, they plant native plants to restore the environment there. So we are interested here in the study the effect of vegetation, and we would like to understand the effect of native vegetation in the problems of slope stability, surface shallow slope stability problems. So we are here with the students, the undergraduate students, just to working around this and to see these problems. Another problems we face in the linear constructions of roads is, for example, this is Bogota, and this is another city that is called Villavicencio. This is one of the main highway, one of the most important highways in Colombia, because around the half of the food supplies comes from this region, from Bogota. So the road is a very unstable road. It is in the Eastern Mountain, as I showed you before. These mountains are composed of sedimentary rocks consisting of a large number of geological faults. It's a geologically of recent formation corresponding to a tropical Andean soil. Primarily it consists of residual soils formed by weather massive. There is some reference here that just to understand the geological formation, but it's very difficult to construct here around the mountains in general in Colombia. So the interaction of different types of soils, alluvial, residual, tropical soils, landslide deposit, debris deposit, among others, makes very difficult the construction. Also, we face intense seismic activity and rainfall activity, that makes the slope stability of the highways a challenge, especially during rainy season. So I would like to show you just a video we take in the October of this year with a visit of the course, of the master's course, slope stability. So we see here a big sliding process, and there was the oldest highway and the new highway that is constructed just to avoid this kind of problems. So we see here two rivers and typical vegetation of this region. This is one of the part that we visit in the highway, but there are many problems like this in this road. So we were there. Because of that, we are very interested in studying slope stability in general in Colombia. So I want to show you two topics to research that we made with master students. The first one is about physical and numerical modeling of clay slopes reinforced with roots. So we work here, me, professor from the Universidad Nacional de Colombia in Manizales, and a professor from the Escuela Colombiana de Ingeniería Julio Garavito that I worked before here in this university. So this is a publication we made in the International Journal of Civil Engineering in 2022. So the presentation is divided in 4 parts: problem and objectives, methodology, results and analysis, and conclusions. The problem we want to study here is the contribution of grass roots on slope stability. The roots of grass improve the slope stability in 2 ways. The first way is there is a mechanical contribution of roots that increases the soil resistance. It can be function also as a little anchors inside the slope. But depends on many variables: root shape, strength, plant age, root depth, root inclination, soil type, among others. This problem has been studied by many research as this one in 2014. Also, the other contribution of roots is the evapotranspiration, as the trees evapotranspirate depending of the climatic conditions also. The soil, the water content of soil decreases and the suction level increases, creating an increase of shear strength of soil. So this factor also depends on climatic conditions, soil type, hydrology, and plant type. We also studied this phenomenon, studying the effect of matrix suction on slope stability. But here we want to study the mechanical effect of roots. This is a very common practice in Colombia. There is specifically one type of grass that we have to do this is vetiver. It's called vetiver grass. And the roots can be very, very long. They are used to control erosion, ecological restoration, and stability of shallow landslides. They commercialized. We can see here the plants and the shape of the roots of this plant. Here we have a figure of this paper, and we see that this grass can reach one depth in only 3 months. So this is a very high growth grass. It's very the the growth of the grass is very fast. So okay. There are some numerical simulations. This is one of this, Gentil 2010. He tried to model the effect of the grass on the soil, on the slope, varying different parts of the growing of the grass. And as a result, there is an increase in cohesion due to the effect of the reinforcement of the grass. So this increase in cohesion produce an increase of the safety factor. Here he made the simulation in finite element test. Also, he found that the critical surface depth of the slide decreases as the reinforcement increases. Also, there are many authors that have modeled this physical modelings in trying to simulate in roots. One of these tried to print with 3D printer, and other ones have planted the real grass or real tree in the soil. But it's very difficult in the simulation in centrifuge because of the scaling laws of soil resistance, morphology, depth, and among others. EAP in 2015 made some tests in centrifuge also in Japan. They mix polyester fiber with sandy soil to find shear strength parameters similar to the reinforced soil produced by grass. So in this research, we analyzed the behavior of a 2D slope varying the depth of the reinforced soil through geotechnical centrifuge. So first, we developed a technique for the construction process. And then we determine the effect of the depth of the root reinforcement on slope stability by analyzing the deformation and displacement on the physical model. So this is the centrifuge of the mini centrifuge of the Escuela Colombiana de Ingeniería Julio Garavito. This paper is described the centrifuge. This is a mini centrifuge having a radio of 610 millimeters. This is a beam centrifuge. It has an acceleration range between 10 and 200 G levels and can support a maximum load in each basket of 12 kilograms. The boxes for preparation of the soils have 17 centimeters length, 10 centimeters wide and 15 centimeters high. This is also consolidation apparatus. So we prepare the model reaching 30 kilopascals of vertical stress, vertical effective stress, consolidating the soil using the Taylor method. And we prepared the 1.5, the liquidity limit. This is there are the properties of the soils. We made an triaxial test to find the cohesion, effective cohesion and effective friction angle. We find an effective cohesion of 5.5 kilopascals and an effective friction angle of 24 degrees. So we mix the kaolin soil, and then after consolidation we cut to reach the geometry of the slope we want to simulate. So we make first the slope without reinforcement. We try to simulate a slope that fails, reaching a safety factor of 0.8 according to limit equilibrium with the Bishop's method. So in the centrifuge, we find many surfaces of sliding surfaces, and we can see here the model scale was 100 and a time equivalent to the prototype to 42 days. This dimension is 7.5 meters, and this dimension 4 meters, and this one 16 meters for the prototype scale. So to simulate the grass, we used fiberglass mixed with the kaolin at the same liquidity limit. Then we mix this, we just put colorant to distinguish the zone, and put like this. Then we fill this part with sand, and then we consolidate again, just to have the shape of the slope. We made 9 models, each depth 2 times, just to verify the model. And then we made a triaxial test with the reinforced soil. We try many times to find the proportion adequate to models to obtain a cohesion similar to the grass. So we have an increase of cohesion about 6 kilopascals and not too much in friction. And at the end of the test, we made in all of these tests that I don't show here. This is just one. We made the analysis of the images after and before the test. We use this software, GeoPaveRG, and we use this line. We just defined this line from the crest of the slope to compute the resultant displacements and compare all the models. So we have here the depth, this depth, and the resultant displacement for all models. So we can see here that the models without reinforcement presents the higher resultant displacement, followed by this one, 0.5 meters in reinforcement, 1 meter, 2 meters, and 3 meters, decreasing the resultant displacement as the depth of the grass increase. So here we can see this figure in other ways to plot. This is the root depth and the resultant displacement. So we can see here that there are like 2 slopes of this figure. In the first part of the figure, the slope is higher. And then after 1 meter of the root depth, the slope is decreased, reaching almost a stabilization of the resultant displacement. And also we can see that this is the depth of the sliding surface that we can calculate here when there is a change in the slope. So we can see here the depth of the sliding surface. And we see that as shown in the numerical models that we see before, it increase. There is an increase of the sliding surface depth. So we made simulations, 2-dimension simulations in Abacus program, because we need to compare the factor of safety with the equilibrium limits method. So we implement the shear strength reduction method in Abacus to find the factor of safety using a Morculum model, and also we use GOE5 program to the equilibrium limit analysis using also Morculum and Bishop's method. So here we have the models, numerical models, finite elements method, and the limit equilibrium method with varying the depth of the. And we can see here that as obtained in the experimental test, the depth of the surface of the sliding depends as the reinforcement increases. So in this figure, we can compare the results obtained in the numerical models with Bishop in limit equilibrium analysis and finite element method, and also the deformation of the crest. So here to compare with finite elements and the centrifuge test. We can see here that we obtained higher deformations in the test with the centrifuge. It's difficult to model it in finite element methods because there are very large deformations in the centrifuge, so there is some error here, but we have same trend. So we find here that at 1 meter about the reinforcement, there is almost we have the same value of deformation of the crest. And also we can see here that the factor of safety increases until 1 meter of reinforcement, after 1 meter of reinforcement. So this is, I don't know. This is the first part I want to show you. The conclusion, I think I already mentioned it. This is the bibliography. I think I have time. And the other part is physical modeling of slope stability of blocking matrix soils. This is Pedro is the master's student who performed this the test, all the test. We presented this presentation in the Colombian Congress of Geotechnical Engineering in November, 5 and 9 November of this year. So as I showed you at the beginning of the presentation, we face many problems because of the geology of the mountains generally in Colombia. We have many materials, a wide variety of deposits that we can consider binary soils, residual soils, mud flow deposits, debris flow deposits, colluvium torrential deposits, among others. For example, this photo is the road Bogota-Melgar, is another city that communicates, another road that communicates with the south of the city, of the country. And this is a torrential terracel. I don't know if the translation is good in English, but it's the result of the transportation of many materials by currents, water currents during rainfall or landslides that produce this type of soils. So we see here many different sizes of rocks embedded in a fine matrix. So for the engineering in practice, it's very difficult to design this. Already when we ask him how they know the parameters to design these slopes, they make a lot of back analysis to find parameters, because doing a test, conventional test in this soil is not representative of the problem, of the size of the problem. So they already know also the values, but it's a very difficult and a question to. Here we see also almost vertical slope here. So this type of soils have been described and studied by mainly these authors, Medley and Napoli in 2021, 1998, and they named it blocking matrix soils to describe these mixtures of soils with rock blocks applied to slope stability. It's well known from previous research that the weight concentration of particles determines the shear strength, as we can see in Vallejo 2001. In the behavior in slope stability is directly related to the increasing volume block proportion. In the triaxial test, we can see from the literature this type of curves. There is a behavior of soil that depends of the weight of the fine and the coarse fraction. So here we can see in this test also depends of the normal stress. So we can see that, for example, here at 40%, there is an increase of peak shear strength that decreases the higher values of the fines content. Also here, we can see these two types of behavior, or here just three types of behavior relating to the amount of the smaller particles. So these mixtures of soils applied to the slope stability have been studied numerically by Medley, Napoli, and Montoya Araque more recently. So they find this is the sliding surface, a circular sliding surface that we can obtain in an homogeneous slope without the blocks. But the effect of blocks produce a tortuosity of the failure surface depending on the amount of blocks proportion. In fact, depending on the volumetric block proportion. Or if we analyze in 2D, the aerial block proportion. There, I just find this physical modeling, but in a 1G test, as in a reduced scale. So we want to analyze the behavior of this slope in a binary soil, varying the area block proportion, using geotechnical centrifuge. So first, our first objective was to develop a technique for the construction process, and then to analyze the formation and displacement fields. So we use same machine as I showed you. And these models, physical models of the slope. This is Medley in 1994 established that there is a characteristic dimension of these types of problems. And in the slope stability is the slope height. In this case, the height of the slope is 3.5 meters, this depth, this dimension. So he suggests that particles that have a dimension higher than 5% of LC are considered blocks, and less than 5% are part of the matrix. If the particles are higher than 75%, rock mechanics should be applied. So we use this to obtain the dimension of the simulated blocks at a prototype scale. We use a diameter of 0.8 meters. This size corresponds to 23% of LC. So just to simulate the blocks, we use aluminum bars that has a density of 2.7 grams square centimeters, cubic centimeters, to simulate the rocks. And we just do these four models, varying the aerial block proportion, 11, 14, 16, and 19. We don't have time to do more simulations, so we just have these configurations. We tried many different techniques to prepare the soils, because it was very difficult, because there is also we have to see the compressibility properties of the soil. At the first step, we just prepare the slope, prepare the soil, mixing with the 1.5 liquidity limit, and then just put the bars inside. But there were we were disturbing the soil around the bars. And we find also cavities. Then we try to just make a hole and extract the soil, and then put the bar, but there were cavities. So at the end of many experiments, we just add first layer, then put the bars, then add the second layer, like this, to fill all the container, and then consolidate all. And we control using a Taylor method to be sure to get the consolidation process finished. In fact, here, the position at the end of the consolidation was not exactly this position, because the soil consolidates. But we can know where are placed each of the bars. So then we consolidate, and then we do the test. You see? No? We can see it again. Okay, this is was accelerated, not was so fast like this. And then we analyze also the photos at the beginning and at the end of the test. All the models we prepared. And we made the analysis, same as I told you before. We find in all the models a rotational failure at the base of the slope. This is the homogeneous one. In all the models, the failure exceeds the toe of the slope. The displacement vectors show greater homogeneity and more defined surface for lower values. And then as the areal proportion increases, there is a variability in the direction of the vectors. And also we can see more heterogeneity in the resultants displacements of the models. This indicates tortuosity and increasing tortuosity as was mentioned in numerical models. Here we did the same thing as I mentioned. So we put this line and we see the variation of the resultant displacement with depth for all models. The blue line is the resultant displacement without bars or blocks. Then, as we increase the amount of bars, 11 and 14%, the resultant displacement increase like this, and there is not so homogeneous like here, that there is some variations produced by the effect of the bars. Then at 16%, we can almost have the same value of displacement as the model with no bars. And then we can find an improvement, less resultant displacement as the model without bars. So we think that this behavior is when there is a few bars, the weight of the slope increases because of the bars. So this produces a higher instability of the slope. But when increases the amount of bars, there is some improvement of shear resistance because of the presence of bars. As we see in the triaxial or shear box test. If we plot here the aerial block proportion and resultant displacement, we can see an increase of the resultant displacement until 12% here. We think that is because of the effect of the weight of the bars, and then a decrease of the resultant displacement. We put just here region 1, 2, and 3 to explain this behavior. With this proportion, we think that there is an interaction between the soils and the blocks, increasing soil resistance and improving slope stability. And in this region, also a higher interaction between the blocks that improves more the shear resistance. So in future work, I would like to do the numerical simulation of this, just to compare the tortuosity and in general the mechanism with the theoretical or with the physical or with the numerical models in finite element. Also, there is many questions here to vary the distribution of the blocks to see to simulate some geological arrangement. So that's the conclusion I already also told you. So this can see.